Well, welcome to a new chapter. We are working on solving systems of equations by graphing. And our learning targets for this lesson is to be able to solve those systems of linear equations by graphing. We'll learn how to do that by hand, but then I will show you also in class how to use your graphing calculator to do that, and also how to use just graphing technology sites like Desmos to do that. Then we're going to learn a little bit of new vocabulary. We will be determining whether our solutions are consistent or inconsistent, and if they are consistent, whether they are dependent or independent. So let's jump in and get started. So first off, a system of equations is just a set of equations. It's at least two, so two or more equations, where they have the same variables. And in order to solve those systems, we need to find an ordered pair that satisfies all of the equations. If there's two equations, that ordered pair needs to satisfy both equations. So we're going to learn two ways to do that. The first is to use a table of values, and then the second is to actually graph each of those equations. So our first example, we have two equations here. Both are in terms of x and y. And it says to solve by completing a table, so I have a blank table for us here. The first thing we want to do is we want to begin by writing each equation in slope-intercept form, and that's the same as solving for y. So get y by itself. That puts it in slope-intercept form. And then we're going to go ahead and pick some values for x. I have those in your table here. We're going to use -1, 0, and 1. And then we'll calculate those values for each equation. So if I put -1 into the first equation, I get out a 1. So that's -1, 1. If I put in a 0, I get out a 2. If I put in a 1, I get out a 3. So those are my three ordered pairs, or the solutions to the first equation. Now I'm going to use those exact same values, -1 into the second equation. That gives me a -5. 0 gives me a -1. And 1 gives me a 3. So the thing to notice here is we got the exact same solution when we put in +1. We got that same ordered pair, and that is the solution to our system. Here's an example where we're going to solve by graphing. The beginning is exactly the same. We are going to start by putting each equation in slope-intercept form, which I have done for you. You solve it for y. Then we're going to go ahead and graph each of those equations. So you can use your y-intercept and your slope to plot points and connect the dots, and then go ahead and graph those two equations. I have the graph for you right here. They seem to intersect at the point 2, 1. So you can use your graphing calculator to help you with that. And then what we're going to do to check that is we're going to go ahead and substitute those two values, x is 2, y is 1, into each equation. So I have the two equations here. When we plug those in, I end up with that, getting 5 is equal to 5 on the first equation, and 1 equals 1 on the second equation. So they both work. I get true statements. So that is definitely the solution to our system. The reason you want to check your answers is when you're graphing these, sometimes if you don't graph using a straight edge and you're just kind of doing it by hand, you might think it's a solution, but you should really check it to make sure that you've graphed it accurately, or use a graphing utility to check your answer. So some real-world examples for you. Systems of equations are used in businesses to determine the break-even point. That break-even point is where your income is the same as your cost. So it helps you determine whether you're going to make a profit or whether you're going to lose money or whether you'll just break even. So here's an example for us. The initial cost for Travis and his band to record their first CD was $1,500. Each CD costs $4 to produce. They're going to sell them for $10 each. How many do they have to sell before they make a profit? So a very practical, real-world example for us. We're going to let X be the number of CDs, and we're going to let Y, and this didn't, I overlapped there, so I'm going to have to get rid of my graph here. Y is the number of dollars, so there you go. So the cost of the CDs is going to equal 4x plus 1,500. It's $4 for each CD times the number of CDs you sell. That's what it costs them to produce the CDs. Plus they've got that flat rate of 1,500. The income is what we're going to call Y. So the income in this one is $10 for each CD times how many they sell. So that's how much money they bring in. This is how much money that goes out. So we want to know, when are those two equations equal? So I have those two graphed over here. Again, you would use your slope-intercept form. They're both in slope-intercept form. Use your y-intercept and your slope to draw your lines, and then find that intersection point. The graphs intersect at the point 250, 2500. That is called our break-even point. So if they don't sell at least 250, they're going to lose money. If they sell 250, they break even. If they sell more than 250, they make a profit. Less than 250, they lose money. So here's our vocabulary for this unit or this lesson, and we're going to classify different systems of equations. We say that it's consistent if it has at least one solution. If it doesn't have at least one solution, we say that it's inconsistent if there's no solutions. Now, consistent systems we break down further into dependent and independent. So we say that it's independent if there's exactly one solution, and it's dependent if it has an infinite number of solutions. So graphically, here's what each of those scenarios looks like. So the two on the left are our consistent systems. They have solutions. There's one solution or there's an infinite number of solutions. So one solution when they cross at a single point, an infinite number of solutions when it's the exact same line. And then it's inconsistent or no solution if the lines are parallel. So let's look at some examples and determine whether our systems are consistent independent, consistent dependent, or inconsistent. Well, we're always going to start out the same way. We're going to go ahead and write our equation in slope-intercept form or solve it for y. Then we can go ahead and graph it using the y-intercept and the slope. Here is your graph. It appears like the graph, they intersect at the point 3, 4. That's a single point, making it consistent and independent. Again, solving for y, we end up with y equals 3/2 x minus 4. And you'll notice in this example, it's the exact same equation when we solve it for y. Well, that's a particular instance where we have one line when we graph it. Even though it's represented in two different ways or two different equations, it's the same line. So that's the one where we're going to call it consistent and dependent, because anything that works in one equation will work in the other one. And here's our last example, solving for y again. We notice that we have the same slope but different y-intercepts. So graphically, those lines are going to be parallel. They do not intersect, so there are no points of intersection. There's no common solution. So we say that that is an inconsistent system of equations. That'll do it for this video. See you in class.